Well, howdy. So I have one more of these examples I'd like to go through. This is one of my favorites, which is the trireme in the water. So, you know, these ancient sailing ships, like the trireme, they didn't have things like, keels. They didn't have jibs. These are both flat sails. You didn't have a nice jib up here to help you with stuff. So it turned out, and this was really true. This was true basically until the Florentines, that you could only go in the direction the wind was pushing you. Now that wasn't really what people wanted to do. A lot of times people wanted to go in the opposite direction. Sometimes they wanted to go perpendicular to the wind. And what did they do? Well, a trireme means that you have 3 rows of oarsmen. So basically they pushed the boat with their backs. That's more or less what they did. So maybe a little bit with their arms, but mostly with their backs. Heave ho, heave ho, heave ho. So that means that you just had to go in the direction of the wind. So if the wind is coming this way, at say 10 meters per second, like it says over there, then you're going to go in some speed this direction, right? So the question is how fast would you go if you had that wind, right? That's what we want to find out. We want to figure out how fast this trireme is going to go. And while you're doing this, what's happening? Well, you've got your boat. Here's my drawing of the boat. It's a little box. Seems like everything in the world that I draw looks like a box. I don't know why. And so you want to go in this speed, at some speed here. You want to figure out what the maximum speed of that is. The maximum speed, you're not going to accelerate anymore, so that's no net force. So this is going to be Newton's first law problem, just like the previous problem. So what sort of forces are on a boat? Well, it turns out that boats have a weight, they have a tonnage, and all that other fun stuff. And then they also have some buoyancy that keeps them from sinking. And we like it when our boats don't sink. That makes us happy. And what's propelling it forward? Well, you've got this wind force here, right? So you have a wind force coming this way, and that's going to be mediated by the sail. I almost drew it backwards. I've been writing backwards so much on that stupid screen at school that life is getting even harder. All right, so that's going to be mediated by the sail. The sail is going to go that way. But the water is also pushing back on the hull. You can see it right there. Well, you can see it later on. But you can see it at the edges. You've seen wakes and stuff like that. The water is pushing back on the hull. So, there's some hull force pushing back the other way. Now, it turns out both of these forces, both the sail force and the hull force, are drag forces. Right? They're both something pushing on the ship, a fluid or a gas pushing on the ship. So in the case of the wind is moving in this direction. So when it hits the sail, it pushes the sail, right? And that's a drag force. All those little air molecules hitting the sail. That gives us a quadratic drag. And then going backwards, every time the ship goes a little distance, it has to push all of that water out of the way, and that creates a drag force pushing the other direction. So this is the direction we care about. Again, we talked about it last time. You can always write B minus W equals 0 because that's what's happening in the z direction. All that's saying is the buoyancy is canceling out the weight. So if the buoyancy cancels out the weight, we're good, right? We don't have to worry too much about it. But on this other spot here, both of these forces are going to be related to the speed. Now, the hull drag, we're going to pretend like there's no water current. So the hull drag is just going to be equal to this number over here, the 16 kilograms per meter. So we'll call that C sub h times whatever the speed of the trireme is squared, because it's relative. The speed relative to the water is what's going to speed relative to the speed of the water, and the water is calm, or the water is still. So therefore, the speed here is just the speed of the trireme. So that's my hull force. But my sail force is going to be that constant for the sail, which is this 1 kilogram per meter, times the difference between the wind speed and the sail speed squared. So that's the relative speed between the air. The speed of the air is the wind speed, right? So all wind is moving air. And the speed of the object is v. So the difference between those two numbers is going to be the relative speed, the speed that is going to cause the drag. That speed difference will cause the drag. So then what we need to do is we need to systematize this. So from the free body diagram, we'd say that the hull force minus the sail force is 0, right? Hull is positive, minus sail is negative. It doesn't really matter too much because signs will come out on the wash. So we'll substitute in these two equations. So we have CH v squared is equal to, or minus CS W minus V squared is equal to 0. But if something minus something is equal to 0, they're equal to each other, right? So we have CH V squared is equal to CS W minus V squared. So then what we have to do is we have to get rid of this bit. So I'm going to eventually take a square root to get rid of the squares, because it's hard to add things under the square. So first thing I'll do is I'll divide through by CS, right? So we have CH over CS here times V squared is equal to W minus V squared. And then I can take my square root, and then I have CH over CS times V is equal to W minus V. Okay, so this is actually probably the point where I'm going to want to plug numbers in, because doing the math at this point makes everything look really complicated. So rather than doing symbolic math, we'll go and do numerical math. So let's go ahead and throw this up here. Right, so CH over square root of CH over CH, CS is square root of 16 kilograms per meter over 1 kilogram per meter. And a nice thing about that is the kilograms per meter cancel. That's times V is equal to W, which we said was 10 meters per second, minus V. Okay, so let's see, what can we do now? Well, we've got these guys canceling. Do we know what this 16 divided by 1 is 16? The square root of 16, we know that one, that's 4. So we have 4 times the velocity is equal to 10 meters per second minus 1 times the velocity. So I add 1 velocity to each side, so 4v plus 1 is 5v equals 10 meters per second minus v plus v, which is 0. So we have 5v equals 10 meters per second, which means that v is, if we divide through by 5, 2 meters per second. And there we are. Not very close to the wind speed at all. I'm not really sure how close those numbers are, so I just made them up to be easy to calculate. All right, so that's more or less what we've done. So we went ahead, we looked at the trireme. First thing we did is we analyzed the forces. We used the free body diagram in the y direction, substituted in the formula for the two different drag forces. One drag force, because you have a wind, is the difference between the wind and the speed of the trireme. The other drag force is the difference between the speed of the trireme and the water current. And I didn't put that in because it makes this really simple looking problem really, really ugly as far as the math is concerned. Then we go through and we transfer the sail to the right hand side. So we say that these two guys are equal. We divide through by CS so that we get only one place with these constants. Then we take our square root because we don't know how to add under the square. And now we have a reasonable thing that we can manipulate without hurting our brains. Then we toss numbers in there. And after that, it's just sort of plugging and chugging, looking at the simplest thing to do at any particular time. So, first taking the square root of the stuff under the radical, and then combining like terms, and then dividing through by a constant. And that gave us the answer, which is not very fast. All right, so there we are. The answer is not very fast, about 2 meters per second. I hope you enjoyed the video. I hope you got a little bit out of it, and I will talk to you next time. Bye now.